Okay, so to start off today, I need you to go to your kitchen and get a spoon. I'm not joking. I need you to go get a spoon. Do you get one yet? I'll wait. Pause it. Go get a spoon. All right, why are we looking at spoons? Because this is probably the best convex and concave mirror that you have in your house because it's reflective. You can see your reflection through it. So I want you to go to the front of the spoon, one where it curves in, and look at yourself. What do you look like? Bring it closer. Further away. What's happening? So you might notice a few things. You're upside down. When it's really close, you're like really zoomed in and much bigger. And then you go further away, and what has happened? You're like more shrunken, right? Okay, but still upside down. Okay, now turn around to this side that's going out, which is convex. Now take a look. You're right side up now, aren't you? Interesting. Weird. Upside down, right side up. Upside down, right side up. Upside down, right side up. So, what else do you notice here when you bring it really close? What does it do? Did you just have like your normal reflection? No, it's stretching it kind of weird in some weird places and ways, right? So, we're going to go over why that happens. All right, so now we're going to talk about reflection from mirrors and how light reflects off mirrors. So, plane mirrors form images that are virtual, appear to be equal distance behind the mirror as objects are in front of the mirror. What the heck does that mean? Well, that just means a mirror like this, that's straight up and down, right? You look through the mirror that's likely in your bathroom, and you'll see something that's the same height as you. It's going to be horizontally inverted, though, right? But you're still going to be right size up, so that's why you're virtual. We'll get more into that and what that means. And then it appears to be basically the same distance behind the mirror as you are in front of the mirror. Okay? So, of course, this is what's happening when you're standing in front of a mirror. Looks like the exact same thing as you is behind the mirror, except for it's horizontally flipped. But when we curve that mirror, things start to get kind of weird. So, as you saw in the spoon, if it's curved, then something's going to change in your reflection. So let's go over a little bit of terminology when we have those curved mirrors. So the center of curvature is the location that would be the center of the sphere if the mirror extended around into a complete circle. And then the distance from C, the center, to the mirror is, of course, the radius, right, of curvature. So we call that principal axis the line drawn through C and the center of the mirror. So something like this, okay? So here we have our mirror, and then of course the line drawn from C to the center of the mirror at A here, that's called the principal axis. And then what's this thing? What's that F stand for? That stands for the focal point. Okay, so that's the midpoint between C and the mirror. So this is halfway in between C and the mirror. All right, so this is half of C right there, and this is half of C right there. So this is the place where all the light rays meet, which is pretty interesting. So we call the focal length the distance from the mirror to the focal point. Okay, so we have C, and we now have F, which is the distance from the focal point to the center of the mirror. And then, of course, that center of curvature is just equal to 2 times the focal point, since the focal point is right smack dab in the middle of them. So when we want to classify that focal point, we need to classify it as real or virtual, which is kind of weird. So a real focal point means that light actually passes through it. So you have a converging image. So that's actually when you held your spoon with the curved side in, you saw that inverted image. That's actually a real focal point. And then the ones where it's spreading you out, the light actually appears to come from the focal point. So that is a diverging image, which is, again, kind of weird to figure out. So we'll get to know that more as we do more diagrams. Okay, so let's go over what a converging mirror is. So converging mirror is a concave mirror, right? Where it's kind of concave like this. That is what a converging mirror is. And so light rays come together through the single focal point. Okay, so all the light rays that come towards the mirror will go through that focal point. So this is our concave mirror, caved in shape, and that's going to be our converging mirror. And then we have a diverging mirror. What the heck is that? That's where light rays diverge and they spread out. So this is our convex mirror like this. How do you know it's spreading out? Well, it's making things appear smaller and you can see more. So you know when you go into a corner store, you see these kind of mirrors up at the corners? That's because since they make light rays diverge or spread out, you can see more of what's going on. So then you can kind of see around the corner a little bit. And that's why they're in stores and things like that. So then people who are working there can see even more, just to discourage theft and things like that. Okay, so that's our convex mirror, and that is a diverging mirror. So when you're looking in these mirrors, you get a real image sometimes, or you get a virtual image. So what the heck does that mean? A real image is where rays actually pass through that focal point. Virtual is where rays don't actually pass through the focal point. Okay, so sometimes you'll have different sizes, right? When we looked in the front of our spoon, sometimes we got a bigger image and sometimes we got a smaller one depending on where it was. And if you hold it the perfect kind of length from you, you can get something that's the same size. And then of course, sometimes the image is upright, sometimes it's inverted. So what we're going to do, we're going to draw these ray diagrams just to see how light rays are going and bouncing off of these mirrors to determine what exactly is the difference between a converging and a diverging mirror, and what's the difference between a real and a virtual image. Okay? So what we're going to do is we're going to draw a mirror showing our principal axis, center of curvature, all that stuff. Then we're going to place a vertical arrow on the principal axis just to indicate like the position and size and the orientation of, the objects that's being reflected. And then when we do that, we need to draw 2 of the following 3 rays. All right, so in these ray diagrams, I'm going to draw 3 possible rays, okay? So the first one is going to be the ray that goes in parallel to the principal axis. So basically, it's going directly towards the mirror, and then it bounces off and it reflects through the focal point, okay? The next kind of ray I'm going to draw is a ray that passes through C and the top of the object and then reflects back along the same path. I'll draw those ones in green. And then we have the ray that passes through or appears to pass through the focal point, and that's going to reflect parallel to the principal axis. So this will make way more sense once I actually start drawing them. So let's just go for it. So for example, we're going to start with a concave mirror, and we're going to start with, what if we had a concave mirror and an object that was beyond C, i.e. behind C? So what if it was back here? So there's my object. So what I want to do is I want to draw the 3 light rays that will bounce off of this mirror in a way that I can kind of depend on. So the first one was when it was parallel to the principal axis and then reflected through the focal point. Okay, so again, I'm going to take my ruler here and it's going to go from the top of the object to the mirror, but it's going to be parallel to the principal axis. It's going to do something like that, okay? And then of course it's going to go from there and it's going to go bounce off and go through the focal point. And it's going to bounce off and go like that. Okay, so there is my first ray and what I know is going to happen with it. Okay, next we have the one that goes through C in the top of the object and then it reflects back along the same path. Okay, so here's the top of the object and then it's going to go through C. So this is actually a pretty big angle here. Now, of course, the mirror doesn't go kind of down this far, does it? So, of course, when we talk about a ray going like this, down like that, and it's going to bounce off, well, this mirror isn't really going that far. So just assume, say it kept going like this, kind of along the same path, then it would bounce off there and then go back up. But of course here, the mirror doesn't go that far. But say it does that, and then it goes all the way back up. Okay, so that's what the light ray through C does. And then thirdly, we have the ray that passes through, or appears to pass through, the focal point and reflects parallel to the principal axis. Okay, so in this case, we are going to go through the focal point. So we have, again, we're just going to draw from the top of the object again. And this guy's going to go through the focal point. If I can line it up properly. So there we go, we went through the focal point and now going to reflect parallel to that. Okay, so I'm gonna do something like that. Okay, so these are intersecting at just about the same place, and that's what we need. And so that's actually telling us what the image looks like. So that's telling us, oh, there's the top of the arrow now. So let's ask what happened to this image. A few things. Well, first of all these light rays are converging, meaning they're coming into one point. So therefore, this is a real image, okay? And that's what it means to have a real image, because the rays are converging. Okay? What else do we know about this? We know that it is inverted, it's upside down. Which, hey, that happened when you looked in the front of the spoon. And what else do we know? It's actually smaller. This one was 4 squares high, and this one is only 3 squares high. So this image is smaller. Okay, which makes a lot of sense. So when you look through a concave mirror like this and you are beyond C, then you will appear to be real, inverted, and smaller. Okay, let's do a few more examples and ways that you could be reflecting off of this mirror. So what if we had an object at C? So say our object was right there. Okay, so again, I want my 3 rays to be able to figure out what the heck's happening. So ray number 1 was parallel to the axis, bounced off the mirror, and went through the focal point. Okay, the other one is the one that goes through C, which in this case, well, that's just straight up and down, right? It's already going through C. So obviously this isn't going to happen, but if this mirror was extended all the way, it would go all the way up and then go all the way back down. Okay. And then finally, the one that goes through the focal point towards the mirror and then bounces back off, but in a way that's parallel to that principal axis. Okay, and look at that. We have our 3 light rays converging right here under C as well again. And look at that. It's also 4 squares as well. Hi, just like the original image was. Isn't that interesting? So what does that mean? What's happening? It looks like it's the same size and in the same position, but it's just inverted, right? So that's what's going on here. We have a real image because, again, our light rays are converging. It's an inverted image because it's upside down. And then it's the same size. Pretty interesting. Okay. next situation, what if we have an object between C and F? We'll say I have an object right there. Okay, so again, I need my 3 light rays and how those are working. So the first one, parallel to the principal axis, hits the mirror, and then bounces off and goes through the focal point. Next one, the one that goes through the top of the object and C. Okay, well that one in this case, it's just not going to happen because we are now in front of C. So I'm going to go right on to drawing the third ray, because really you only ever have to draw 2 of the 3 to know what's going on with the image. Okay, and so then that third one was the one that goes from the top of the object through to F and then bounces back off parallel. There we go. Okay, so these guys are intersecting way down there. And so what do we have? Well, again, we have a real image because these are converging. Again, if they intersect like this, they are converging. But of course, we do have our inverted image. But in this case, it's larger. So this is likely what's happening when you're looking through the spoon. Okay, is that you're looking at it from a situation where you're in between the center of curvature and the focal point. Or it could be that you're looking in front of the focal point, but it's going to be something like that. Okay? Another example is when our object is at F. So we're going to draw an object right there, and I want to know what happens here when an object's at F. So again, what are our 2 rays? Well, we have the one that goes parallel here, bounces off and goes through the focal point. We have the one that goes through the top of the top of the object in the center of curvature. Ooh, look at that. So it goes with the mirror, bounces back off, and goes back that way. Okay, I'm not even going to draw the third ray because look at that. What just happened? That blue and green line, what kind of lines are those? Those are parallel lines. Are those ever going to intersect? If they never intersect, what do you think is going to happen to the image? There's no image. So if you find the perfect focal point of a concave mirror, you'll disappear for a sec. But you got to find that focal point like right perfectly, and then you'll see no image, which is pretty cool. But yeah, these light rays are never going to converge, so they do not create an image. And then of course, what happens if our object is between F and the mirror? And let's go over that situation. Okay, so there we go. There is my object. Okay, so gonna draw my 3 rays. First one, parallel to the principal axis. And then of course bounces off and goes through the focal point. Okay, the next one that goes through the top of the image and the center of curvature. Let's go through that one. Okay, so again, it goes towards the mirror, bounces off, and goes back out that way. And then we have our third one that goes through the focal point. Well, here it can't really go right through the focal point, but it can look as if it's coming from the focal point. So just line the top of the arrow up with the focal point. Okay, and then I'm going to draw that like that. And then, of course, that's going to go parallel to the principal axis. Okay, what do you notice here? Are these three lines going to intersect? Well, they're definitely not going to intersect on the left side of the mirror. So what the heck is going on? This is what we call a virtual image, because guess what? The light rays look as if they're coming from behind the mirror. So that's that situation. So we just need to sort of dot back here. I'm not using the ruler right now. I'm so sorry. It does make things kind of difficult. But there we go. So I know it's a bit wonky, but you guys get it. So they are actually going to diverge back there. So look at that. We have an upright image, but this image is virtual because the light rays actually diverge and therefore kind of come together behind the mirror. But what's really happening is it looks like the image is coming from behind the mirror. Okay, so there we go. There's our first virtual image, because the light rays diverge instead of converge on one point. This is also our first upright image. And then, of course, we have a larger image here. Okay. So there we go. That's what happens when it's between F and the mirror. So that's a very different situation for a concave mirror. Now, one more thing, I just want to do a convex mirror. Now, with a concave mirror, it really depends where you are in terms of C and F. But when you're in a convex mirror, this side of the mirror is the reflective part, right? The right side is. So the points C and F are on the other side of the mirror, the non-reflective side. So really we only have one option here, and that's to be in front of the mirror. So thankfully we're not going to do a bunch of different mirror diagrams. For convex mirrors, we're only going to do one, because there's only one way to be in front of a convex mirror. Okay, so of course we're going to do one where we are in front. So I'll go right about here. Okay, and so these ones are going to be a little bit different, because again, the focal point and the center of curvature are on the other side. So remember, our first one was when it was parallel to the central axis, which is pretty easy, but then it's going to reflect, and it said it'll go through the focal point, but here it won't go through the focal point because of course it's on the other side of the mirror. And light rays don't really go through mirrors very well. So it'll look as if it's coming from the focal point. So you can probably already see that it's going to diverge. So just to be proactive, I'm going to dot back here, because I already kind of feel like this is definitely going to be a diverging image. Okay, the next one was the one that goes through the center of curvature. So again, this one's not going to go through the center of curvature, but it's just going to appear to kind of go there and then back. Okay, and again, going to dot back here. And then our last one was the one that goes through the focal point and then reflects parallel. So again, we're just going to line it up and make it look as if it's coming from the focal point. Okay, and then how is it going to reflect? It's going to reflect back parallel to the axis. It's going to reflect like that, but again, we're going to dot back. Look at that, we got where it converges, and of course it converges behind the mirror. So this is truly a diverging image. But like I said, with these convex mirrors, it always creates a smaller image, right? So again, we know that this is a virtual image because it's from diverging light rays. It is an upright image, right side up. And it's smaller. So there we go. That's what's always going to happen with a convex mirror, no matter where you are in front of it. So we don't have to do any more light rays for convex mirror. But that's what I'm talking about when I'm talking about light rays. So where all those rays intersect is actually what the image is going to look like. So that's what that's telling you. So a few patterns that you may have noticed. Real images are always inverted and virtual images are always upright. So that's one thing that hopefully you did catch on to. So we do have this mirror and lens equation, and this is on your data sheet, and that is 1 divided by the focal point should equal to 1 divided by the object of the distance from the mirror plus 1 divided by the distance of the image from the mirror. Now, this is the one time we can all just kind of work in centimeters, or it could be all meters, or it could be all millimeters, because as long as they're all in the same unit, it really doesn't matter. So there you go. Just a note, real focal points are positive, virtual focal points are negative. The distance of the object from the mirror is always positive, but when we have real images, since they are on the same side of the mirror, they're going to be positive. But virtual images, remember, those are images that look like they're coming from behind the mirror, and those are going to be negative. And oh boy, those positives and negatives are going to be really, really important when it comes to this equation, because it will get you a lot of different answers. So please, please, please know this. Okay. Okay, another equation that you can look at is this guy right here. This is also on your data sheet, and that is magnification. So basically, how much is something being magnified? So magnification doesn't have any units, but it could equal to the height image over the object height, which also equals the negative of the distance of the image to the mirror divided by the distance of the object to the mirror. So you can also, of course, make the M equal to the H's, or the M equal to the D's, or the H's equal to the D's, or whatever. Remember, it's a 3-part equation here, so you can choose whatever 2 parts you want. That negative sign is just necessary for sign conventions. Just remember, magnification is always positive, okay? So that negative side can float, kind of be written on either side of the equation. So if you get a negative, then you just move to the other side. But it should always work out as long as you, again, obey these rules here of negative and positive images, okay? So let's just go over an example really quickly with using these new equations. Okay, so we have an object that's 2.5 centimeters tall, placed 9 centimeters in front of convex mirror that has a focal length of 4 centimeters. So what was the convex mirror again? Is that the one with the virtual or the real focal point? This is a convex mirror. It has a virtual focal point because the focal point is behind the mirror. Okay, so that's going to be really, really important. So please note this focal point right here, that is negative 4.0 centimeters because we have a virtual focal point. Okay, so we're just given the height of the object, and here we're given the distance it's placed from the mirror. So I want to determine the image characteristics. So basically, what's the height of the image? What's the distance of the image to the mirror? So let's start with the image distance, because I think that's all we really can start with. And that's with this equation. Okay, so to find the image distance, of course, I can just subtract 1 over DO from both sides. That gives me 1 over DI. But what I need to do is I need to take the inverse of that. Okay, so if I really want the image distance, I need to take 1 over F minus 1 over DO. And I need to take the inverse of that whole thing. Please, 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 please do not think that DI is just equal to F minus DO. That's not how inverses work. That's not how applying exponent to subtraction works, okay? So you do know that for math, but people tend to forget it with this equation. So I just had to point that out, okay? So let's figure that out. So our focal point, remember, is negative 4.0 centimeters. And then minus 1 over, the object distance was 9.0 centimeters. And then, of course, we're going to take the inverse of that to get our image distance. And we get an image distance of negative 2.8 centimeters. Why is it negative? Because It's virtual. That's exactly what we expected. Okay, so that's really, really good that we actually got that. So we know this is virtual. Awesome. Let's go on to the height. So in this case, again, I don't really care about magnification, so I'm going to use these two parts of that three-part equation that we got. Okay, so if we're looking for the height of the image, that should be negative di times HO divided by DO, which we got all those. So remember our image of distance from the image to the mirror was negative 2.8 centimeters. The height of the object was 2.5 centimeters. And the distance of the object from the mirror was 9 centimeters. Okay, so we put that all together. Our height is 0.77 centimeters. So it's positive. What does that mean? Means that it's a virtual image again, which we already figured out. Okay, awesome. It means that is it smaller or bigger than the original object? The image is smaller, okay, right? Because the original was 2.5 centimeters. So that's what you would expect from a convex mirror, right? So we know it's virtual, we know it's upright, and we know it's smaller. And that's exactly what we expect from a convex mirror. Okay, let's do one more. So example 2 here, we have an object that's 20 centimeters from the mirror. So that just gave us our distance of the object to the mirror. It has a magnification of 1/3. Okay, well, it just gave us magnification 1/3. That produces an upright image. Okay, so we have two situations if we have an upright image. Again, if you're trying to remember when would we get an upright image? Well, either when we were using a convex mirror, we got an upright image, or when we had a concave mirror, but the object was between F and the mirror. So we have one of those two situations here. We got to figure out which one is happening. So we're going to determine the type of mirror, is it concave or convex, the image distance, and the focal length of the mirror. Okay, so what's the first thing we can do? Well, in this case, we just have the magnification and the object distance from the mirror. So we better just start with this equation right here. Okay, so if I want the image distance, then that's just the magnification times the distance of the object from the mirror. Oh, I forgot the negative out front. Because I know the distance image is going to be negative if we have an upright image, because that means it is going to be virtual. So we already know that. So image distance equals negative 1/3 times 20 centimeters. Okay, so we get an image distance of negative 6.67 centimeters. Okay, so there's our image distance, which again doesn't really tell us much at this point. We still don't know if it's going to be concave or convex. And of course, we can only find that out by finding the focal point. And if the focal point's positive, it's going to be concave. And if it's negative, it's convex. Okay, so then we're going to go to this equation because now we can use it. Okay, and then we're going to find this focal point. So we just need to take the inverse of this whole thing. So 1/DO is 1/20.0 centimeters minus 1/, and then again, these negatives are so important. Please do not forget. Okay, and then we're going to take the inverse of that. That gets us a focal point of negative 10.0 centimeters. Oh my goodness, negative focal point. So what kind of mirror is this? Well, we know that we get a negative focal point when we have a virtual focal point. When do we have a virtual focal point? When it's behind the mirror. So this must be a convex mirror. Okay? Okay. Did we figure out a type of mirror? Yes. Image distance we got focal length of the mirror. We got, okay, we figured this out. Hope that helped you guys. I know it's a little bit different. So again, make sure that you are practicing the things in the workbooks, because it is really, really important. Because now tomorrow I'm going to throw lenses into the mix, and then it's even more confusing. So make sure you do practice a few of these before you watch the lesson on lenses. Good luck.